gave before was absorbing transitions and evolving the same. I have two comments on that. One is I'm not convinced Wall Street is really an absorbing transition, and it seems lunch might be. Okay, so here's an outline of this lecture in one slide. So you can watch this slide and then you can go back to it. So of course, what we're really dealing with in this talk is the non-equilibrium state with reversible transition. So this is familiar experience of entropy, integration at time zero, and that's all I'll say about entropy. So the question that I'll address is if you tune the parameters of the system in the right way, can you cause irreversibility to suddenly appear as if it was through a phase transition? And I'll tell you the answer, which is yes. If so, what kind of phase transition is it? I'll present evidence to you that it is consistent with an absorbing phase transition. The results I'm giving here are fairly recent, so we don't have concrete proof that it's really an absorbing phase transition, but there's lots of suggestive evidence that it might be. And finally, the last part of the talk, I wanted to show you that an irreversible phase transition of this same type, whether it's really absorbing or not, appears to be generalizable to another phenomenon, specifically to the phenomenon of plastic deepening. So I'll give you a brief introduction of what I mean by this and why it would be really significant if plastic deepening turned out to be an absorbing phase transition. Okay, now I'm going to, like in my last talk, show you several systems to illustrate my point. And just to keep you from getting lost, here's a roadmap of the three systems that I'm going to explain to you. The first system is not my own work. This is the work that inspired the work that Reichhardt did. And so this is colloids sheared in what was supposed to be a Stokes flow machine. So this is both experiment and simulation that was performed at NYU. Then the two systems that I worked on that were inspired by this, the first one is a version of this for superconducting vortices, and I won't reintroduce that system. I'll assume you remember that from yesterday. If you don't, then just ask me. So we'll take vortices steered back and forth over quench disorder so that they actually have very much the same properties. And then the third system will be plastic deepening, but in that case it will actually be for colloids on quench disorder. And again, this should be general for any type of plastic deepening, including the vortices and the resistors. So those are the three systems. One other comment, I am a theorist, because someone asked me yesterday about my bacteria experiments. No, I don't do the experiments. Okay, so now let's actually go through these different systems. And let's start by considering a situation where you would naively expect that the system should be irreversible, and it turns out not to be. This is a famous old experiment. I have a problem with my quick time here, which is reversibility in a viscous flow. So this is a famous experiment that T.I. Taylor originally produced, I guess, which is essentially reversibility in a low Reynolds number flow in a viscous liquid under shear. So this is a movie you can grab off the internet. They have it on the NYU site. So what they have here is a Couette cell, which is two cylinders, and you rotate the inner cylinder and the outer cylinder is fixed, and that applies a shear to whatever you've got inside. And what they have inside is a mixture of a relatively long, high molecular weight polymer. And what they're going to do is add some dye, add a spot of dye to this, and then rotate the cylinder first forward 4 times, and then backward 4 times. So this runs for about a minute. So here's their system. They're putting the dye in at this point. I'm just going to make one spot of dye. And one of the significant things about this system is that thermal fluctuations are on this time scale are insignificant. So there's no diffusion of the dye molecules, and that's actually relevant to what happens. So here he's going to come in and rotate this around 4 times. So what you see is this spot is totally done. Now you would naively expect, okay, that's it for this spot. The spot's done. There's no way to get the spot back. But obviously I wouldn't be showing you this if that were true. So after he finishes going around this direction, now he's going to turn around and go back in the opposite direction 4 times. So it seems that nothing's happening. Here's once, and here comes the second time. And still nothing. Third time. And finally, on the 4th time, here he comes. So he's almost gone as far as he did originally. Now you can see, if you watch, here comes the spot. Right back.
And how do we know we didn't just run the film?
Actually, when I was at graduate school in Michigan, one of the fellow students built it. It's fairly simple to make. And then he took it around every single other graduate student. Look at this. So it's actually, and after a few days, it does start to diffuse a little bit. But So this is an example of, you thought it should be irreversible, but it was reversible. Now, question?
So what was being rotated?
So the inner cylinder.
Yeah.
There's two cylinders. So there's this is the top view. Here's the outer cylinder, and the inner cylinder. The outer cylinder is fixed, and the inner cylinder is attached to this thing. So he's just turning this around, and it's rotating this inner cylinder.
And the polymer was in between the two?
Yeah, the polymer is in here.
Okay, thanks.
Very viscous.
Yeah, this is extremely, and that's important. This is extremely low Reynolds number. So even though this seems surprising, it always seems surprising because you're not used to seeing systems that obey Stokes law. So let me give you an introduction to Stokes law. You're familiar with systems that obey Navier-Stokes law. And so this is the Navier-Stokes equation. You have several terms here. You have inertial terms where there's an unsteady acceleration term for your fluid, and then there's a term coming from the convective acceleration. And then on the other side, you have the stress terms. You've got a pressure gradient and a viscosity. But in this system, we have extremely low Reynolds number. What is Reynolds number? It's just given by the ratio of the inertial force to the viscous force. So if Reynolds number is really low, it means that the viscous force completely dominates, and you don't have any inertia, which is similar to the Brownian dynamics simulations I was showing before. Bacteria and other things like that live at low Reynolds number. So if you have extremely low Reynolds number, you can neglect both the unsteady and the convective terms and the Navier-Stokes equation, and that gives you just the Stokes equation, which is simply the pressure gradient being proportional to this viscosity term. This equation is linear in both velocity dependence and pressure. It's instantaneous. It doesn't have any time dependence except through the boundary conditions. So that means if it just sits there, nothing will happen. And most importantly, it's reversible. So if you take a solution to the Stokes law and then you time reverse it, it's also a solution to the Stokes law. So that's why if you go forwards, you have one solution, and you go backwards, it's the same solution, you get right back to the same state. So this is fairly unusual in such a large and complicated system that you would have truly reversible flow. So what the group at NYU did, so let me go back to my roadmap. Now I'm going to tell you about the experiment that the NYU group performed and show you some of their moves. Their idea was, well, let's take this Stokes law system from the Taylor experiment, and let's put some colloidal particles into our cell so that they can be like little probe particles. And then we'll share it back and forth, and we'll look at what happens to these colloids. Does the system still remain reversible if we do this, or does it become irreversible and go back to more of a Navier-Stokes kind of a situation? So Pine et al., Pine's the first author, and Chaikin and J.P. Golub were also involved in this experiment. Looked at this reversibility. Again, here's the Couette cell. Here's the inner cylinder, which they'll be rotating, and the outer cylinder, which is fixed. And here are the colloids. They, instead of going around several times like in the Taylor movie, they're going to take their inner cylinder and just rotate it back and forth, and they'll choose the amplitude of that rotation. So they'll either go a really far distance or they'll go a short distance, and they can vary that. And they don't go super fast, so this is relatively slow. And they measure the position of the colloids at the end of each shear cycle. So they're really taking a stroboscopic picture. They basically take the system, rotate it as far as they want, rotate it back, and then take a picture. So if you did that with the Taylor experiment, you would just see that spot, and that would be it. You wouldn't see anything else happening. When the behavior is reversible, the colloids come exactly back, well, almost exactly back, to their same location after each cycle. There's a little imperfection in the experiment. So let me show, this is a lame animation. Let me show you their movies. First I'll show you what their system looks like without the stroboscopic view. So this is what they've done is they've set up a camera pointing this way at the edge of their cell. And then they can either run it in a continuous movie. So this is what the colloids actually do as a function of continuous time. Is first they're going one way, and then they're going back the other way. You can get an idea of the magnitude of the oscillation they put. It's much less than a full rotation in this case. They're just going back and forth some fraction of their whole cell. And this is, of course, just one little slice of their whole cell. So now they don't use that to take the imaging. For the imaging, if I can get it up here, now they take a stroboscopic picture. So this is the same system again, but now they're just taking a picture once per cycle. And so what you see is not much. If you look closely, the colloids are moving a little bit. But basically, they're always coming back to the same spot. So these are colloids going out here and coming back, going out and coming back. So this is the reversible regime.
Looks like something is happening on the
Well,
back,
there's
because that's our
some
focus.
kind of shadows that go through, and I guess that has something to do with their imaging. It's not relevant to the physics they're looking at.
Okay, so we're not actually seeing the out of focus stuff from the other side.
Well, yeah, this might actually be colloids that are kind of out of plane of the focus of the camera, but it's not. You should look at the ones that are in good focus here. Okay. So that's the reversible regime. But then they said, all right, let's turn our inner cylinder further on each cycle and see what happens. So let's try to do the Taylor experiment, go around a whole bunch of times. We still get it. Well, it turns out that if they raise the amplitude of their strain, then they lose the reversible behavior. So here's the same type of stroboscopic image, but now at a higher strain rate.
Question?
Yeah.
What's the fluid?
In their experiment, again, it's a highly viscous fluid, but I have to refer you to their experiments. I don't remember what it was. It's some large polymer. I think it's either the same one that Taylor used or it's something. It's a high molecular weight book.
So it's a high amplitude of the strain rate. What's the highest strain rate?
The highest one that they applied?
No, I'm asking what's different.
Bigger amplitude. Bigger amplitude, yeah. So they're going back and forth further now.
Okay.
So before they were going, just a little bit.
Okay,
And now they're going further.
Same frequency?
Everything else is this. Well, let's see. Did they change the amplitude? I think they keep the strain rate the same. They just go further. So I don't think they go a further distance. It takes longer, but it doesn't. That's the amount of time it takes isn't that important because thermal fluctuations are negligible in the regime that they're in because this is such a viscous environment. Okay, so let me show this again. And here you see this is extremely different than the previous movie. Now, when they are not coming back to the same spot, they're teetering all over the place, almost like they're experiencing thermal fluctuations. So, in fact, they can measure the mean square displacements in the two directions here. This is in the direction of shear along x, and this is perpendicular to that direction, which for them is z, it's up and down. And you can see that their mean square displacement as they accumulate strain in the system, sort of like time, increases with time. And so they can define an effective diffusion constant from that. So what's happened is they went from a system that was showing this reversible Stokes flow to a system which is now irreversible. So this is indicating that somehow Stokes flow has been violated. You can't have irreversible Stokes flow, right?
Just to clarify, the x-axis is the different amplitude. You do this.
Oh, on this, here this is like time. So this is the number of cycles that they've done. So if you take the original position of the particle and then you oscillate once, twice, 3 times, 4 times, it gradually goes further and further away from where it started out.
Is it linear?
Linear? Let's see. Here they've got it plotted on a logarithmic scale. So, yeah.
So it's really diffusion-like and not drift-like.
Yes, that's right. Yeah. Another
So
one?
it is linear?
What's that?
It is linear?
I said that this is mean square, and therefore
Yeah.
mean square being
Linear.
linear means it's actually diffusion-like.
So it is linear?
Square, yeah. RMS is
X squared is
square.
linear, x is square root.
Okay.
Yeah, thank you.
So
Okay.
is that isotropic?
No, it's not isotropic. So this is in the direction of shear, and this is perpendicular to the direction of shear. So it's an anisotropic. It's an anisotropic diffusion. They're diffusing more. So this is time traces over many. Just looking at the stroboscopic pictures and doing a time trace like that, you can see that they tend to move more this way than this way, which makes some sense.
What about the third direction?
They didn't have a way to measure that. They were just looking at it in the 2D, and so they couldn't probe whether they probably were going in and out of the y direction, but they didn't measure it. It's a relatively thin cell, but it's not vanishing thin. Okay, so the question is, they didn't change the Reynolds number, so they didn't leave the Stokes flow that way. So what did change? Well, you can get a clue by looking at the conditions under which they see this behavior. So first of all, they know that if they have a low strain amplitude, they get reversible behavior, which means that the diffusion coefficient is not defined because they're not diffusing. And then there is a threshold where suddenly you start getting diffusion, and then as you increase the strain amplitude, the magnitude of that diffusion goes up. And again, it's anisotropic. Here's in the direction of shear, and here's perpendicular to it. The threshold strain that you have to apply to get diffusion to start decreases with increasing colloid volume fraction. So they started with relatively few colloids in their system, and then they made the colloids denser. And then depending on this volume fraction, they go from having to apply strain amplitude of 12 all the way down to where they only have to apply maybe strain amplitude of 1 before they get the onset of this irreversible behavior. So obviously, in some way, interactions between the colloids are playing a role. Okay, so that's setting up the system. They've done a number of measurements and also some simulations on this, which I'll show you. Yes?
So, I guess, can you tell me more about particular colloids that they used?
Once again, I believe they're probably polystyrene spheres, but I would have to refer you to
Are
the...
they uncharged?
Oh yeah, these are in the uncharged one. Yeah, so they're not. You think of these as just sort of hard spheres, not significant.
So these are just hard spheres?
Yeah, in fact, that's how they model them. Just
Deforming
as.
the Stokes law? Or what?
Say that again.
Hard spheres deforming the Stokes law, and then there's a hydrodynamic interaction?
Well, okay, so that's the question. What is the nature of the interaction that's between the colloids that increases when you raise their density? They actually, when they do the modeling, they leave out hydrodynamic flow, and they're able to capture this effect. So you can get it in a different way. Okay, I'll talk about their simulations in a minute, but let me first ask some questions about the results that I've shown you so far. So first you can ask, well, all right, you see this for colloids in this Taylor experiment, essentially. But you can ask if you have similar reversible transitions in any other particle-filled viscous media. Is it special to the colloids? Do you need the hydrodynamics? Or can you get it in systems that don't have hydrodynamics or other types of interactions? And kind of how universal is this behavior? The next question, which I already told you the answer to, well, possibly, is whether this reversible-irreversible transition is a non-equilibrium phase transition. And if so, what is the nature of that phase transition? Or could it even be a non-equilibrium phase transition that looks like an equilibrium phase transition? And finally, can you get similar behavior from vortex matter and type 2 superconductors? Okay, so now we'll go to the second system, and this is now going to be work that I've been involved with. And we're going to try to model the colloidal system with vortices. We're going to drive them back and forth with quench disorder. So as I told you yesterday, superconducting vortices have no mass as far as anyone can tell. So they're essentially in an extremely viscous medium. You can think of them as being in low molecular flow. So in principle, they could obey Stokesian dynamics, and you could get reversibility.
Doing simulations on a colloidal system is not practical? Or?
So this wasn't done in a good pedagogical way. We just happened to do it with vortices, and then we actually returned to the system and did it with colloids, but not in the exact experimental geometry. Okay. So my claim is that the behavior is general enough that which system we picked doesn't matter so much. But for publication purposes, it was better to do it with the system. All right, so here's our system. As I showed you yesterday, we're going to be working with overdamped equation of one for the vortices. Vortex-vortex interaction is once again modified Bessel function, so we're assuming that there's stiff vortex lines, so the fluctuations in the third direction are not important. We're going to have the vortices interact with a random background of pinning. And the way we're going to represent this is just we're going to take some parabolic wells that have a finite range. Question?
Are you still doing this at zero temperature?
Yes, this will be at zero temperature, so there's no thermal fluctuations here. All the fluctuations are going to come from interactions between the pinning and the vortices themselves. So that'll be C. So we're going to represent the disorder as just parabolic wells that have a finite range, because otherwise you get an infinite force from them. So we just chop off the attraction of parabolic wells at some radius, which is constant for all of them. And we sprinkle them down randomly on the system. We do anti-correlate them, they can't sit on top of each other. And they all have a fixed strength. And then we apply a square wave driving force to the system. So we simply take the vortices and we push them all to the right for some period of time and then push them back to the left for a period of time and just repeat that. And we will vary this period t, and also the driving force, and we will vary, so the magnitude of this, and we'll vary the strength of our pinning and the density of our vortices. Okay, and from yesterday's lecture, although we're breaking time reversal symmetry here, we aren't breaking any spatial symmetry, so there's no. Okay, so let's start by varying the displacement per cycle. So we're going to vary the combination of the driving force times the drag. So we're going to change how far vortices go back and forth in each drag cycle. And we're going to measure a quantity which is essentially the same quantity that they measured experimentally. They did it experimentally by taking a snapshot every time the cell went back and forth. What we'll do is we'll look at the position of each particle at time t0 plus n times the period, where n is an integer, and we'll subtract from that the original position of the particle at time t. And we'll look at that in both the x and y directions. It's supposed to be a hat here, where alpha is x and y. So we'll define this in both the x and y directions. And from that, just like the experimentalists did, we'll define an effective diffusivity in both the x and y directions. For us, the y direction is like their z direction, because we're shearing the system back and forth along x, and they will also be looking at displacements transverse to that. So the effective diffusivity is just going to be this measurement divided by times the amount of time that was elapsed. Okay, so here's the similar version of what you saw for the experiment, only shown for our simulations. What we're doing is we're taking the positions of our particles during 25 cycles, and I'm showing you where the particles are marked every 0.01 tau. So every 1/100th of a period, I might just spot where the particle is. And this is just to convince you that the vortices are actually moving back and forth. Now, if I do the same thing, but I mark it at every period, you see that nothing happens. All the vortices start at one spot, go out, and then return exactly to that same spot. So this is a reversible regime, and this is where the displacement per cycle was 48 lambda, where lambda is the penetration depth, lemon penetration depth. It's the unit of length in our simulation. Now, if we increase the displacement for our vortices per cycle, we see just what the colloidal experiment sees, which is that we enter an irreversible regime. So here's once again 25 cycles, just the same as I showed you before, marked every period. But this time the displacement per cycle is 160 lambda. And there's not more particles here, they've just moved around. And you can kind of see they tend to move in lines, indicating that they've got more displacement in the direction of the drive than perpendicular to it. And if you keep going, if you wait longer and longer times, you just cover up more and more of the sample. So you're getting a sort of diffusion everywhere through the system. Question?
Is there a reason you have the frozen defects in here? I mean, was there something similar for the colloids? Sorry,
Oh, you mean the pinning?
The pinning thing.
Well, okay, if we don't put random pinning in there, nothing happens. Because we'll just have, there's nothing, so in the simulation, there's nothing special about one spot of space compared to another. So our vortices will just form a triangle S and they'll smooth in a triangle S. You have to have some kind of mechanism for some smooth. And so we do that by putting in these pinning sites.
And is there an analogy in the
In
colloid
the colloid system, what's happening is the colloids are just bonking into each other. They have a hard core. Our vortices don't have a hard core, so they can't. What's that?
It's a solution, right?
Well, yeah. So you also have the fluid around the colloids, which can give you.
I think isn't it just break down gallium, whether you break gallium there or not?
Yeah, that's right. Yeah. So unless we put pinning in our system, it does nothing. It just goes back and forth. It's triangle. So we have to have pinning to get anything from those questions.
What's the determinist or selection?
Yes. Well, so since I don't have any thermal noise, it's just this equation of motion, and that's it. So it's just depending on the positions of the other vortices and the positions of the pinning and then the driving force. So there's no stochasticity in the equation of motion. Okay, and I can show you brief movies. They're not very exciting. They're not quite as nice as the experimental movies. Here's the reversible regime. You can see we've got one vortex that decided to kind of go cruising around. But basically all the vortices are just coming back, and it's an extremely boring movie. Question?
I just have kind of a question. So how do you interpret typically the friction coefficient of the circulation?
Oh, for the vortices? Yeah, I don't have it. I can show it to you, but it's eta is
you have
proportional.
no thermal noise. I'm just having a hard time visualizing how do you explain the nature of it.
Also, where does it originate? Well, you can argue that it comes from the scattering of the electrons off the phonons in the material. I've seen different descriptions of where you microscopically get this
There
data
isn't
from
like an
it.
agreed upon story. It's just a phenomenological fertility.
Well, I mean, there's a well-defined value for eta, which is related to the upper critical field of the material and the normal state resistivity of the material. So I can show you that expression. And then at one point I looked into this a little bit, and it's been too long, so I'd have to relook at the literature. But there was a little bit of an argument of exactly what eta came from. So when you really got down to the nitty-gritty of what's bonking into what to do the dissipation. But I think essentially you could say it's dissipation of the normal electrons in the core is probably the best way of looking at it. Okay, and then here's our same system that this time where we've increased the amplitude of motion of the vortices. Now this is sort of more exciting and less exciting. Now they're jittering around a lot. So this is very much like what they saw in the experiment. Yes?
So in the irreversible regime, have you looked at correlation functions?
Yes, so let me now show you some real measurements. You're saying lengths and times?
The correlation between...
Yeah, so let me show you what we
correlated.
measured. Yeah. Another question?
Yeah, so just in that movie, it just sort of looked like they were oscillating about their same position.
Oh, you can tell that?
Well, I mean, it's much more
Well, so there's some, so for instance, these guys aren't moving so much, but some of these, I mean, I can't really tell where they're coming back to. It depends on the magnitude. But this is, just looking at this isn't a very good way to measure it.
Yeah.
Let's actually measure it. So what we do is we measure this quantity which I told you, which is how far if we look after n periods, how far away from its original position has the particle gone, and then we increase the number of cycles. And so this looks like what you would do for a diffusion measurement. So we're measuring an effective diffusion constant. And so here's what we get for x direction motion in the direction of drive. So this is increasing the time. And then here's what we get for y direction motion, also increasing the time with a reduced magnitude. So this is consistent with having an anisotropic random walk, and that's very much what they had in the experiment. And then we can extract from that effective diffusivities, dx and dy. And here you see the anisotropy of dx and dy both increase as we increase the distance that the particles travel per period. Dx increases pretty rapidly, dy a little bit more sluggishly. Also, just like the experiment, we see a threshold. So if we don't push the vortices back and forth far enough, we stay reversible. And then there's a fairly sudden onset of irreversibility.
Is it in the left panel? Is it implying R squared? Because it looks like slope 1.
Slope 1.
It's diffusive.
It's diffusive, yeah.
So it's implying R squared.
Yeah, definitely. Okay, so now we can look at how this varies with a couple of different parameters. Just like in the colloidal experiment, they varied the density of their colloids. So we can vary the density of our vortices and see what happens if we make more or less vortices. What we find is if we have very few vortices, so now we've just fixed the displacement at some value that's large enough to be in the irreversible regime of what I just showed you. If we lower the number of vortices in the system, we'll actually drop back into a reversible regime. So now they're getting so far away from each other that they just don't care anymore, and they'll always go back to the same spot. As you raise the density, they kind of abruptly develop this finite diffusion. And if you keep raising the density, the diffusion actually gradually goes away. And of course, what's happening is that the vortex-vortex interaction is becoming more and more dominant, and eventually just wipes out the pinning. So we're no longer able to induce relative shear in our lattice, and we'll just go back to having the lattice go back and forth.
That's gradual. There's nothing.
Yeah. So that's so actually here's what happens if you get out far enough in NV. So this is beyond the edge of this plot. We actually get a little bit of a smectic regime right at the end, where they stop moving in the transverse direction, but they're still moving in the longitudinal direction. So we're getting some relative shear in a smectic-like state. Let's see. And the threshold here for the drive, the amount that we have to displace them as a function of the vortex density in order to induce this transition, just like in the colloidal experiments, drops schematically. So as we increase the density, we have to shear them less and less to get them to go irreversible.
So what, it's hard to decide. So what fraction of the particle spacing of the critical
Oh, it's
displacement?
actually, so this is actually significantly larger than the particle spacing. They're moving a lot of lattice constants here. So like 200, I mean our whole system I believe is 48 by 48 lambda.
Is it 2-dimensional density or what?
Yeah, this is all
Yeah,
2,
yeah,
this is 2 dimensional, that's right.
On the left plot,
The left plot?
Yeah, how far do they move when they start to show reversible behavior?
Oh, here, this was at a displacement per cycle of 96 lambda. And then we varied NV. And then this is, where does this fall, what drive does this point, let's see, how do I say this? If we do this then as a function of drive at different NV, where does this point fall? So that's this point here.
Was your density of hitting sites always the same?
We fixed that, yeah.
So what was that?
Let me see if I have that on here. I did not put that down. I'll have to get back to you on that. It's relatively dense, but not everywhere. So it's probably about 1 per lambda because we often use that.
What's lambda?
Lambda is the London penetration depth, and we just use that as units of distance.
But there are many more pinners than vortices.
Well, so we vary that. We go from the limit where there are a lot fewer vortices than pins to where there's more vortices. Like we go both sides. Okay, finally we can vary. So we keep the number of pins fixed, but we do change their depth. And if we do that, you can see once again what you would expect. If we make the pinning really weak, we lose the irreversibility because once again we can't induce any shear. And then there's once again a threshold where suddenly we pick up this irreversibility. And then as we make the pinning stronger and stronger, we gradually start to lose the irreversibility again. Because actually what's happening is they're having a harder time moving. And eventually they'll just all be stuck in the pinning. Question?
Here in this figure and in the previous figure, the dx, dy, it will increase to a maximum point and then decrease. Is it due to the interaction between the colloidals?
Oh, okay. So like I said, here, the fact that this goes through a maximum is because out at high FP, everything's stuck again. And at low FP, it's not shearing. So there has to be a maximum in between those 2 points. And the same thing for this one. At low NV, nothing's interacting with each other. At high NV, it turns back into a triangular lattice and doesn't interact with the pinning. And so there has to be a maximum in between those. We didn't study where exactly this maximum would fall, so we didn't try to predict that. Okay, so now I can see that we're getting really good at reading between our vortex system and the colloidal system. So we're seeing this diffusion-like behavior in the X and Y direction as anisotropic. We're seeing that as we increase the distance the particles travel, this diffusion increases and there's a threshold. And then we're also seeing that as we increase the density, that threshold decreases.
Excuse me. How do you make a comparison here since you
Okay, this is a qualitative comparison.
No, but you don't have pinning in the colloidal system.
Yes, exactly. So that's why I'm saying it seems that even though these really aren't the same systems, the behavior that we're getting is very similar. So we're trying to claim that actually there's something universal going on here, that these systems that you might think there's no reason that they should behave the same way are giving us very similar behavior. Other?
The slope equations are reversible in time.
Yes.
And there you get irreversibility, that's a surprise. But here you take more time equations.
Yes.
Is it a surprise that you take irreversibility?
Actually, it's almost more of a surprise we got reversibility, but not really. I mean, if we make the interactions weak enough, we're going to get irreversible. We're going to get reversibility. What's interesting is the fact that the way that we go between those two states is very similar to the way that this system goes between those two states. That actually wasn't expected, and that was the surprise in this system. I mean, we wouldn't have tried this, and we didn't think there was some hope that would be true, but we didn't know in advance that it would look this similar. You first.
How did the vortices move around from cycle to cycle? Do they stay somewhere near the pinning sites, or do they, at the end of a cycle?
Well, so it's very similar to the movie I showed you of what the Colloids did, which is it starts here, and it goes way over here, and and then it comes back.
Yeah,
so they
no,
don't,
no, I mean in the stroboscopic picture.
Oh, well, I showed you a movie.
Yeah, but
it's hard to tell.
I didn't really see where the defects are. Are they?
Oh, I didn't show those in the. Yeah. So the vortices are at that density, they're pretty much sitting in the defects at the end, but not 100%. You can have vortices that are sitting in what's called interstitial pinning. In other words, the pinning is random, so there are spots where it's clustered and spots where there's no pinning. And so if you've got pinned vortices and there's a spot with no pinning, a vortex will still sit there and actually be pinned just because of the repulsion of the other vortices. So some of the vortices are not in pinning sites, but they're still pinned. They'll find an energy in them. Okay, there's a question in the back?
Yeah, is the only randomness of an energy model in the initial conditions and the placement of the pinning sites? Because you don't have any thermal fluctuation.
Well, so the other thing that happens is you have very complicated interactions between the vortices themselves.
Are they velocity dependent?
No, they're not velocity dependent. I mean, it is deterministic.
It would seem to me, based on that if you drove it with the right frequency, your system would be completely deterministic.
Yeah, and that's what we see. If we don't move the vortices very far, they'll come back perfectly to the same spot.
No, I'm not thinking about distance. I'm thinking about frequency.
Frequency. Let's see. Is this going to be frequency different? Since this is overdamped dynamics, it shouldn't be sensitive to frequency because when you do overdamped dynamics, the positions of the particles tell you everything. There's no inertia. So if I just take a snapshot of my system, I know all the forces that are present. So doing it faster or doing it slower actually doesn't matter. I'll get the same results here for this system. What's happening is as you go a further distance, the vortex is having a chance to interact with more vortices along its path. And the chance that there's enough of a rearrangement that when it comes back, it doesn't actually get back to the same spot. That's what's occurring with the interactions here.
How does the randomness enter then? If it's preset that it interacts with some vortex and some inside, when you start moving the...
Well, so I mean, one way, so this is now actually asking the question, where does irreversibility originate? So I can make the argument that the system starts to become very sensitive to slight changes in position. So, if I start the particle here, and there's other particles that it can interact with, it'll take some trajectory, but if it had been just a little bit further down, it would actually have gone on a different trajectory. So that's one way of arguing where this is originating. We can, I'll talk to you more about that. Okay, so now let me talk to you about absorbing phase transitions. So these are the signatures that we have. Our system is reversible at low displacements and irreversible at larger displacements, reversible at both low and high densities, and irreversible at intermediate density, and then similarly reversible for both weak phase disorder and irreversible for strong and just went in for really strong. So we're going to claim that this transition is consistent with an absorbing phase transition. We haven't done proper finite size scaling to really prove this, but we're going to present evidence. You have a question?
So you mentioned that pinning is important for the irreversibility to occur, but you just said that it's all due to the basically binary collisions of the vortices.
But you won't have, so you have to get relative shear between the vortices for what I said about the collisions to occur. I mean, if you don't have any pinning, I just have a triangular lattice without any relative plastic displacement. So I have to have some kind of plastic displacement for my argument that I gave you to apply. So that's where the pinning comes into the vortexes. You don't need the pinning for the Colloid system. It's a different mechanism there. Question?
So you seem to be suggesting that the irreversibility is coming from sensitive components to initial conditions. So have you measured the outcome exponents?
No, actually we haven't. Yeah, it turns out that measuring the outcome of exponents in a system with this many free particles is not, and in a continuum, is not an easy task. So we didn't attempt it. But that would be one way that you could try to test it. So like I said, I mentioned that in the very first slide, but I'm not really going to address where does the irreversibility deeply come from at a deep microscopic level. I'm just going to say, this looks like an absorbing phase transition. So let me briefly, I don't know from your t-shirt whether you assume that you all know everything about absorbing states now and say anything, or if I should cover it. So the absorbing state is, of course, a configuration which can be entered by the system, but can't be left. That's why I'm not convinced that Wall Street is really an absorbing phase transition. But the most important, so there's many types of absorbing phase transition, but the most important universality class of this type is directed percolation. And so, of course, the common example of this is percolation through sites which have directed bonds. So here's an example of regular percolation. I have a lattice that's been tilted on an angle here. And with some probability T, there's either a bond between neighboring lattice sites or there isn't. And if I put a drop of water at one of these sites, I ask, well, it's going to follow all possible bonds. Am I going to get an infinite cluster that'll go all the way through the system or not? And there's a transition as a function of my probability P, whether I'm going to get an infinite cluster. In the case of directed percolation, now I make all the bonds directional. So one way you can do that is take this system and then put gravity. So now I say, well, things can only flow down, they can't flow up. So if I put my spot of liquid here, it can only progress downwards, it can't go backwards. And so I've actually broken a symmetry between space and time in this system. This hypothesis is actually used a lot in the spreading of infectious diseases because if you have some transmission of I'm just going to use the swine flu. if I have influenza and I transmit it to you with probability alpha, I can only do that forward in time. I can't, if I catch the influenza at a later time, I can't go backwards in time if I interacted with you and give it to you then. So I can only give infections to people I haven't met yet. At any rate, you have two states then in a system like this. You can have an endemic infection, where there's just always somebody with influenza, and that's the fluctuating state in this system. Or you can have a case where the infection dies out. Finally everybody's caught it, or the transmission probability is too low, and finally somebody doesn't pass it on, and it's just gone. And that's the absorbing state because, of course, once the flu is gone, it's gone. So that's what we hope smallpox will do. So there's a continuous phase transition between these two states, and there are diverging correlation lengths associated with this. Now, it turns out the way that these correlation lengths diverge has been calculated with various techniques, but it's not known exactly. And surprisingly, there is almost no experimental realization of directed percolation. And that's very surprising because it's such an important model theoretically. Let's see. One other comment about these directed percolation systems. They do not obey detailed bonds. These are inherently non-equilibrium processes. Okay, so now let's look at some critical exponents for these. As I said, these are not known exactly, but they are known from various transitions. Did I put this reference? Yeah. If you want to know lots more about directed percolation, here's an excellent review, and I won't try to pronounce his name in case I get it wrong. Okay. So the order parameter in directed percolation is going to be the density of active sites. So how many of the sites are either moving or have an infection or so forth, and we'll call that relative T. And so as you approach the percolation transition, that density is going to vary with the power law. So here P would be, for instance, the probability of having a bond between two sites. So P minus BC raised to the power of beta. And then since there's an asymmetry in this system, there are actually two independent correlation lengths. One is called the spatial correlation length, and the other is called the temporal correlation length. So if this is a picture of a directed percolation process, here's time and here's space. The spatial correlation length is going to be how fat are these in this direction. And then the temporal correlation will be how extensive are they in this direction. You can see that they don't necessarily need to be. In fact, they aren't the same. And so these will have exponents associated with them. This is the spatial exponent, nu perpendicular, and this is the temporal or nu parallel. And you can also define a dynamical critical exponent, which is just the ratio of those two. And one of the reasons there's no theoretical version of these exponents is that the directed percolation is not conformally invariant. There is not symmetry between space and time, and this makes it very hard to treat theoretically. Here are the values of the critical exponent. I'll just flash them now, but actually I'll come back to this slide because I'm going to be comparing what we're seeing with what people get in DP, and we're going to be looking at the two-dimensional case. So if you can memorize really fast, you can save yourself, or you can just look ahead in my notes. Okay, so I mentioned that in spite of the importance of directed percolation, there's actually been almost no experimental realizations until very recently. There's actually been one. This is a group at Tokyo who measured the transition between two topologically different turbulent states. They took a complicated system, which is electrohydrodynamic convection in a pneumatic liquid crystal. Essentially, they took this pneumatic liquid crystal, put it between two plates, kind of like a convection experiment, but then they applied an electric field, and then they get turbulence, and as they change the as they change the magnitude of the electric field, they can switch from a state which they call a dynamic scattering mode 1, where there are few disclinations in the pneumatic crystals. And then they can change over to this dynamic scattering mode 2, where there are many elongated dislocations. And so they can easily see which of those two states they're in, and they can observe a transition between the two. So they measure the activity of the phases. One of the reasons that this is a realization of directed percolation, and there's hardly any others, is that this system has extremely low disorder. What people have found is when they try to make a realization of directed percolation, any small amount of disorder in the system kills off the transition and you can't see it. So this happens to be a beautifully clean system, and they were able to see correlation exponents that were consistent with directed percolation. So here's their order parameter, which is how much the system is in the DSM-2 state as a function of how much voltage they're applying. And they see a sudden onset, and then a decrease. And if they look at how this increases as a function, they have to do V squared rather than V because it's actually dielectric torque driving their system. They get an exponent beta of 0.59. And you would expect an exponent beta of pretty close to 0.59. I mean, this is, considering the nature of the experiment, this is really good agreement. So now we can say, all right, well, we have kind of a model for, there's finally been an experimental realization of what looks like directed percolation. What does our system do? If we go back to our vortex system and look at, and call our order parameter this dx, and look at how it varies as we approach the critical threshold for driving vortices back and forth enough to get the irreversible transition, we can extract an exponent beta, and we also get beta of 0.59. Again, we haven't done finite size scaling, but we see this similar exponent. Question?
Yeah, I'm sorry, did you say something about how you fit the data?
Oh, here?
Yeah.
Okay, so yeah, how did we determine the critical
because
point?
it looks like the points with the smallest error bars have the largest deviation.
Let me see. So we are furthest away. Yeah, so you don't expect scaling to be obeyed as you get far away from the transition. So you wouldn't, I mean, these points are more important. And of course, they're harder to get, so that's why the error bars are bigger.
So do you just throw those points out?
So we weight these, I mean, when we do the fit, we just concentrate more on these points and don't worry. You can't fit them all. So we just try to fit as many of the lower ones as we can.
Okay.
And like I said, to do this really carefully, you need to do finite size scaling. We haven't done it really carefully. Okay, so the shearing system shows behavior consistent with the global phase transition, not proof. And we asked, well, is there any additional evidence supporting the nature of the transition? Can we generalize the transition? So I'm about to go into our third system here. But let me talk to you about time-dependent quantities that are associated with directed percolation. So I showed you 4 exponents so far, but I can define 2 more exponents. You can look at the value of the order parameter starting from a fully occupied lattice. So basically you're looking at a decay. And you expect that should decay with some exponent alpha. And alpha is simply going to be given by beta, your order parameter exponent, divided by new parallel, the time-like exponent. And then similarly, the survival probability that your cluster is still active after t steps goes like t to the negative delta. And delta is given by beta prime over new parallel. Beta prime is simply the probability that a randomly chosen site belongs to an infinite cluster. And in directed percolation, beta actually turns out to be equal to beta prime. So alpha and delta are the same. All right, so now let's look at 2 things at once here, which is, first I want to describe to you briefly the simulations that the NYU group performed to try to explain what was happening in their experiment. And then I'll explain what we did with some plastic flow simulations. So what they did is they set up a colloidal simulation, and it's a very simple simulation, and it doesn't even have that many particles in it. They just said, let's take our colloids, and let's have them have essentially a Lennard-Jones interaction. They don't know about each other. If they get close enough together, they kind of bonk off each other. And that's it. And then they're going to take these colloids and just shear them back and forth. And then, of course, there's viscosity. So what they see is that as they do snapshots, they look at how many particles are sitting in one spot, and then they color those white, and how many particles are kind of moving around as you're oscillating back and forth. And they look at that as a function of how many times they've oscillated the system back and forth. And I believe that their simulations are actually able to get out to much more oscillations than they can do in the experiment. So here's a case where they're shearing at a rate of at a distance of 3 in their units. What they find is that, the number of particles that are still moving, deviating from where they originally started, just sort of stays, it never goes to 0. It kind of goes down, but there's always some particles that are moving out of place. Whereas if they lower their shear rate, now they've moved back and forth less distance, over time they get to a state where everybody has stopped moving. So they look at the decay from their starting state as a number of cycles, how many particles are active, essentially. How many particles are getting displaced from their position. And if they're at low shear rates, they see this decay fairly quickly down to where nobody's active. Whereas if they're at the higher shear rate, they see it decay some finite value, where there's just always some particles that are active. And so you have your choice. Either you're in the absorbing state or you're in the fluctuating state. And you can see how long it takes you to get to that state.
So the number of cycles is 2,000. Does it say here? The number of cycles, it takes 2,000 cycles for it to reach equilibrium. But
in this case, yeah, in this case.
But experimentally, so they would...
Well, I don't think they matched this parameters to their experiment. They just want to show that this model has similar behavior to their experiment. Yeah, I'm pretty sure they don't get their experimental numbers because their model is too simple. But it gets some nice behavior, which is they can see the existence of a diverging time scale to reach that steady state. So there is some threshold which they've seen in their experiment before you switch from having everything be reversible to having everything be irreversible. But as you get close to that point, the amount of time it takes for the system to decide which side of the transition is on goes up and up and up quite dramatically. And so, you have to wait a long time before it's decided, well, has it really settled down? Or is there going to be a moment where suddenly the last moving particle stops moving? So it just takes a lot longer and longer to find that. And if you look at the scaling of this, you get an exponent of 1.33 for this diverging time scale. That agrees well with what you expect in directed percolation for the time-like exponent. There's a mistake in the notes. This is supposed to be time-like exponent 1. Close to 1.29. Okay, so now let me go to our final system, which is plastic decomposition of colloids on French disorder. And I'm going to claim that this system has exactly these same properties. So first let me talk to you about plastic decaying a little bit, and why it will be significant if it is one of these absorbing phase transitions. So here's a picture of plastic decaying. What we have is colloids on a random substrate. And now instead of pushing our particles back and forth, we're just pushing them in one direction as a function of time. And we just increase the force. So first we push them only a little bit, and they don't go anywhere. As you push them harder, they start to move, but they don't all move. Some of them move, some of them don't move. And they start moving in these complicated channels, which can form and break apart with time. And eventually at high drive, everybody moves, and you're back to an elastic regime. Plastic decaying is very general. It occurs in vortices in type 2 superconductors. You can see it's friction system, charge density waves, Figner crystals. A lot of systems undergo this type of behavior right at a decaying transition. And there's currently no theory for the nature of a plastic decaying transition. So what I mean by plastic flow is very simple. If you think about having a rough landscape that your particles are sitting in, maybe one particle is in not such a deep spot, and one particle is in a very deep spot in the landscape. And here it is in 2 dimensions. So suppose this particle is really stuck, and here this particle is trying to come up behind it, sees that this particle is in the way, well, simply go around that particle and pass it, like having a broken down car or something in your lane. So what this means is that 2 particles that started out being neighbors don't necessarily remain neighbors. The distance between 2 original neighbors diverges with time. So the lattice distorts into pairs. This is completely non-elastic, and particles can actually move. You're driving them this way, but they can actually move perpendicular to your direction. Now, as I said, there's no theory for plastic decay. There's some observations about it. If you increase the driving force and look at the velocity of your particles, you find a shape like this, which is extremely general. And if you look at this on a log-log scale, you can fit this to an exponent of just about 2. So that means that the velocity is going like the force squared here. There's no explanation for why it should be 2, but all we know is that we see 2 a lot, and a lot of other groups see 2 a lot. In contrast, you can have what's called elastic depinning, and so here's where the particles keep the same neighbors at all times, and then they can distort a little bit, but they don't tear as they depin. And this is well understood. You see the curvature is actually completely different here. As you're approaching the depinning transition, you get an exponent of 2/3. And this has been explained. So elastic depinning is understood. Plastic depinning, not understood. Okay, so we're going to now do a colloidal simulation. So I showed this system to you yesterday. We're once again putting our particles on a random substrate, just like we were doing with the vortices. But instead of swashing them back and forth, we're just going to turn on a drive. And we're actually going to turn on a drive and see whether, we'll turn on some drive and wait, and see whether the particles eventually all keep moving or whether they eventually all stop. And we're going to define those to be if some of them still move, that is our fluctuating state. And if they all stop, that's an absorbing state. Because of course, once they all stop, that's it. We don't have to keep running the simulation. Nothing will ever happen again. And these are some of the longest and largest simulations we've done. We ran up to 17,000 colloids, and we ran these for 2 months. So these are very big, and this is one of the reasons we didn't do kinetic scaling. So what we do is we suddenly apply a force, depending on the strength of the absorber. So if we were just going to fix the magnitude of our force, we're going to make the pinning either weaker or less, stronger or less strong. And so as we look at the function of time, what the particles do, here's for the pinning strength of 0.3. We suddenly apply our drive, and over time, some of the particles get stuck in a pinning, but some just keep moving. So it looks like this is a fluctuating state. Here we have a slightly stronger pinning. We apply the same drive, and fairly quickly, everybody gets stuck. So this is our absorbing state. This is our fluctuating state. Now we do measurements where we look at how long does it take to reach a steady state. So here we've applied our drive suddenly. We measure the velocity of the particles, which is proportional to how many of them are still moving. And we see that decay away. And then at some point, it'll reach 0 if it's a pin state, or it'll go to a finite value, which is still fluctuating, some plastic full state. And the colors are reversed here, but this is very much what Corte et al. Saw in their simulation. Either you reach the fluctuating state or you reach the pin state. And we're going to fit this curve the same way that the experimentalists did with this exponential function to extract a time scale.
How is you might have said that the pinning was defined, is it a bounded distribution?
The pinning. Oh, so this is the same as, I don't think I put it in this slide. We just have some random distribution of these steps, which we keep fixed. We're changing the strength.
But the depth is, when you say FP.
Oh, yeah, so we have parabolic pins, so let's see, here's your potential.
You just vary the number, you don't vary the...
We don't vary the number, we just make them deeper. That's all. So as a particle, as a colloid enters this, it feels either more or less force. And that's, we keep the size of them the same, we keep the spatial distribution of them the same.
And so what is FP?
FP, this is the depth of the line. So it's the strength of
It's the maximum depth?
Yeah, so it's the maximum, so
they all have
let
the
me
same depth.
show the force here. Yeah, the force is just going to be, let me draw it the right way, like this, right? Where this FP is basically what you experience.
Right, but they're all the same FP.
They're all the
they
same.
have random positions for the same FP.
That's right. We didn't do distributions of FP.
Well, that's a
Yeah, I mean, it's one more parameter, so we just put them all in the function. Yeah. Okay, I'm running out of time, so let me quickly show you that what we get is very similar to what Corte et al. Get, except I think it took us a lot longer because our simulations were a lot bigger. We see the same diverging length scale as you approach this critical FP, where you pass from the particles. If FP is too large, the particles will all get pinned for a long time. Whereas if FP is smaller, they'll continue flowing in the plastic flow regime. And so this diverging length scale, if we fit it to an exponent, we get an exponent of 1.36, a little bit bigger than what they had, but still not so far off, considering this isn't the best measurement, from the timeline directed percolation.
Driving force on that scale? The driving force on that scale?
On this scale, driving force, let me see, it's actually going to be, let's see if I have it on there. It's going to be, kind of not that far from this point.
It's not right at P?
No, it's not right there. It's because there's some disorder. Yeah, I'll have to show you afterwards.
that the same one?
Oh yeah, here we go. Okay. So yeah, it's below. The driving force is actually way down here. Because we don't want to, we wanted to stay in the plastic flow regime. If we raise FV, we'll actually go to elastic flow. And we're not interested in that. Or else, no, if we keep lowering FV, we'll have to have a transition from plastic flow to elastic flow. But elastic flow is already understood. Okay, so we're getting this agreement with both the Colloids simulations and with directed percolation. We can also look at the decay of the number of moving particles as a function of time. And right at the transition, we see a power law decay, which we can fit to an exponent of 1/2. And this is the exponent that you would expect, this value you would expect for directed percolation. Actually, there's something called conservative directed percolation where this should be 0.45, but I don't have enough time to describe that to you. Okay, so this is what we're seeing, as I showed you. We're getting good agreement with this directed percolation exponent of about 1.295 for the time-like exponent. For the decay exponent, we're seeing 0.5, and this is also consistent with directed percolation. So that means that this phase transition is consistent with these directed percolation models in 2+1 dimensions. So our claim is that plastic depinning could actually fall into this universality class of an absorbent phase transition. This would be exciting because there's lots of experimental measurements of plastic depinning. So if this is true, you now suddenly have this big class of experiments that could in principle show you directed percolation behavior, rather than just one extremely specialized experiment on turbulence in an electrohydrodynamic system. People have never suggested this before, so nobody's ever looked with all this plastic depinning data. So now we're trying to pester all the experimentalists to see if they can, try this type of analysis on their plastic depinning data. Okay, so this is finally the summary. Basically, I'm trying to claim that all these seemingly different systems which have these transitions between a fluctuating light phase and an absorbing phase are actually maybe falling into the same universality class of these absorbing phase transitions. And perhaps this is giving us insight into the nature of plastic depinning. So thanks for your attention.
Questions? Yeah?
So I still didn't understand the origin of the randomness in the first colloidal system. Was
the original colloidal system?
Yeah.
The NYU experiment.
Yeah, the Quet flow. Was it just, when the material gets to some kind of yield stress, the way it deforms is less predictable?
So what they claim based on their simulations is that it's actually due to collisions between the colloids. Because when they reproduced their experiments with their simulations, they did actually a pretty simple model, which is just hardcore interacting colloids with no hydrodynamics or anything. And where this reversibility or irreversibility came from in their simulation was just when they would walk into each other on the way past. And then that would displace them, and when they came back, they wouldn't rebond in exactly the same way.
So it is sort of analogous to your vortex simulation in that the interactions is...
Exactly. That was perfect.
Yep.
So how could they collide in the first place?
In reality, there's going to be a little bit of the polymer in between, right? Is that what you're saying?
If you have an initial condition, if it's really a hardcore collision, then if you drive it back and forth with a time symmetric equation, then they will always stay apart. Except for the initial...
So you're saying where does the relative shear come from? Well, I think it may be just because this is a finite width, and that it's actually... So there's not really a truly constant shear here.
But in their simulation, this puts in at the initial condition where they have a linear joint.
So in the simulation, these are starting close enough together that they're sort of already pushing each other out of the way.
Because they've got a linear joint instead of the hardcore interaction. So it's all initial condition driven then.
Well, I guess you could claim that. I mean, in Stokes flow, that's what you would expect. But, I guess maybe we could discuss a little bit more of the microscopics of their model.
Just on the next slide. If you take hydrodynamics flows at lower Reynolds number, even 3-particle dynamics is known to be chaotic.
Yes. Yeah.
It could be chaos rather than just bumping of particles.
In the actual system, yes.
In the
Yeah,
actual
absolutely. Yeah.
I'm still somewhat confused about the vortices and how they're pinned during the simulations. If they do diffuse, right? So do they hop from pinning site to pinning site? Is that how
Well,
it is?
so what they do is they get out of the pin. So it's not a discrete process. I mean, if here's my pinning, then if a vortex gets out of this pin, it doesn't immediately run over to another pin. It'll move through a free region at first.
Yeah.
And, it should, so let me put a pin in its way. If there's another pin here, maybe it'll get to this pin. Of course, since all our pins were the same strength, in principle, if it hopped out of this one, it would also hop out of this one. In practice, the pins aren't really the same strength because of the presence of the other vortices. And that elastic interaction makes some pinning less effective than other pinning. So maybe it'll stop in this one, maybe it won't. Whether it does or doesn't might depend on whether this vortex is exactly here or exactly there. And that can actually sensitively change it. And this is the sort of thing we've already seen a lot in plastically pinned, or just plastic flow. We've looked at that quite a bit in the past for the vortex system. So we know how these channels of flow really change a lot with time. Even though you might expect they would form and then be constant, that's not what we see.
So, but stroboscopically, it is sort of a hopping.
Yeah, so stroboscopically, they're going to hop from minimum energy site to minimum energy site. So it may not really be from pin to pin, but it'll be from pin to interstitial pin back to pin. Yeah.
Okay. Go ahead. So
I was just looking at your plots for the sudden application of force for different disorder strengths. It looks like you're getting shear bands. Would you agree with that?
In the vortex system.
Yeah.
This one, shear band. Well, so what we get is plastic channels.
Yeah.
And it's not called shear banding in this system, but it's essentially like shear banding. I mean, we're localizing the flow. And in fact, I've alluded to the fact that we have problems doing finite size scaling for this system. And there are two reasons. One is we already did a really big system. This is actually only part of our sample. So we did this huge system, and one of the reasons we had to do a huge system is if you do a tiny system, it becomes very unstable to the formation of these. And you'll get these channels really easily. So the way to avoid that is you have to make your system big, and then they tend not to form unless they really want to form. So we can't go to smaller sizes without destroying what we're trying to look at. But we keep going to bigger sizes because it already took us months. So we haven't been able to do finite size. Maybe the next generation of computers, we can do that.
There was a question.
Just about the numbers for these pinning sites. Your radius that they captured in is much smaller than the average data.
Yeah, I believe we used a radius of 0.2 nanometers. So these are relatively short range. And whereas the average spacing is usually something like 1 lambda, although we vary that. But the average we never go through a regime where there's going to be more than 1 per pin. So they're small enough that there's always at most 1 particle trap per pin.
If you drove the system with the time reverse protocol for the driving force and showed us a movie of that, would that look the same as the original driving?
Time reverse protocol. So for which system? For the plastic flow?
Any of them.
So how would I do that? You mean if I took this system and I drove it backwards? Or
the ones where your time reverse, where the protocol is like a step way.
Oh, if I reverse the direction of the step. Is that what you're asking?
Yeah, the time reverse.
Let me see. So in the irreversible state, I think the microscopics would be different because you're starting. I mean, they're sensitive to where they start. So if you're driving them backwards first and then forwards, it's going to be a little bit different than if you drive them forwards first and then backwards. But you're still going to be irreversible. Is that your question, or?
Yeah, I mean, statistically, it could be distinguished between the two movies.
In principle, well, statistically, or you mean like if I followed the detailed motion of one particle? I think the answer is you would distinguish it because it's not reversible. So, I mean, you would be able to tell if I drove it backwards compared to forwards.
So when you drive,
at least you would tell that they were different.
So when you have one driving protocol, let's say when you start with the forward direction going first to the right, particles tend to go to the right more often than to the left.
Oh, so you mean for the diffusion? I don't think we measured that. I don't believe so. Yeah, we didn't test that. Because this is going to be, there should be an average, and I may have forgotten to put it in the, yeah, this should be, I believe I'm missing an absolute value here. So we didn't look at, we just looked at the total displacement, but we didn't say, you know, they're on average drifting away. Because there's no average, you wouldn't expect them to drift in one direction. So I don't, but we didn't measure that explicitly.
I think what you're referring to is something that I observed too when you showed us the stroboscopic plots for that. Looked like them randomly hopping back and forth, and I tried to view that same movie backwards, and it looked identical. But that's not the issue. You still have diffusion that goes. I mean, the mean square displacement is still growing in time. It's not shrinking or something. So although if you kind of just stare at the pictures, it may look superficially the same.
I asked because I was a little confused about the definition of irreversibility.
Yeah, so in this case, what we're doing the same thing as the experiments is we're saying once you have a non-zero effective diffusivity, that's what we call the irreversible phase. So basically, once they start leaving the area that they were returning to, then we say that's irreversible, whereas if they keep coming back to the same spot, we call that reversible. So that's our definition in this system.
I guess now, I think the same confusion that Jordan has is that if I run the movie backwards, so in the diffusive regime, if I run the movie backwards, do I get back to where do I get the reverse trajectory?
My claim is no, they would actually not go back. They wouldn't follow the same path in the irreversible regime. They would follow a new path because there would be.
But you would see the same diffusion.
Yeah, exactly. Yeah. So, like I said, this
but you would see a different trajectory going back.
Still
okay.
see
That's. I think. Is that what you're saying? Yeah. I think that's
a little more subtle.
I might have a slightly surprised that you just conserve DP as very large.
Oh, well, so, yeah, that one, and like I said, I decided to leave that because it got kind of confusing. Actually, the reason that we were looking at this, there were two reasons. One is that there was a paper claiming that the Corte system is actually conserved directed percolation and not directed percolation. And actually, I got these backwards. Conserved directed percolation gives you an alpha of 0.5, whereas directed percolation says alpha of 0.45. In practice, these are so close to each other that it's almost impossible to tell them apart. In fact, CDP has a scaling anomaly. So alpha and delta ought to be different, but they aren't. So, because beta and beta prime are different in CDP and the same in DP, but alpha and delta are equal. So that's just an anomaly. And so it was sort of I was like, okay, let me, and then it was on this slide, so I forgot to take it up. But yeah, so I think we cannot, we can barely say whether it's really any kind of directed percolation. We certainly aren't going to distinguish between these two, but it's possible. Yeah, but it's, you can make an argument why it would be conserved directed percolation because we have a constant number of particles. And that was it was a Japanese group I could find a reference for you. But I didn't include that in here.
Okay. Further questions? If not, let's thank Cynthia again. The next session is a short